In today's video, we will establish the following relationship between the sizes of three different infinite sets. We will show that the cardinality of the set of natural numbers is strictly less than the cardinality of the open interval from 0 to 1, which actually has the same cardinality as the entire real number line. I find this relationship quite interesting because it shows that there are different kinds of infinities, some larger than others. Before we begin, let's begin by recalling the following definition, which is about cardinality. So cardinality in mathematics is a term that refers to the number of elements in a set. It's better to use cardinality than size because size could refer to many different things such as the length of a set or maybe the area of a set, but cardinality is the proper term that refers to the number of elements in a set. And so we say that two sets A and B have the same cardinality if there is a bijection between them. Let's take a look at a few examples to make sure we understand what I mean by bijection between them. So here is an example of two finite sets. A is the set of weekdays and B is the set of numbers 1 through 5. Now looking at this, you might say, well, they have the same cardinality because the first set and the second set, they both have 5 elements, and you did this by counting, right? And I would actually encourage you not to think of cardinality in this way. You do not want to count the number of elements explicitly. What you want to do instead is actually make pairs. You want to make correspondences. So let's say we make a pair of Monday and 1. We make a pair of Tuesday and 2, and so on. And in the end, you see that we have nothing left over. We have nothing left over in either A or B. So this actually shows that A and B have the same cardinality. If we had, let's just say, an extra number left over or an extra weekday left over, then that would actually indicate to us that one set is larger than the other. This way of thinking helps us when we start looking at infinite sets. So for example, if we look at the set of natural numbers and the set of even numbers, these are both infinite sets. There's no way you can sit here and count all the numbers. What you want to do instead is actually create a correspondence. So you want to map 1 to 2, 2 to 4, 3 to 6, and in general you want to map n to 2n. This way, every single even number in this set will have a preimage, right? Something that maps to that number. And also, distinct inputs map to distinct outputs, right? So this is just in words saying that this function is a bijection. It's both injective and surjective. So moving forward, we want to think of cardinality as creating this pairing, this one-to-one correspondence between the elements of two sets. Now let's take a look at another definition that differentiates between countable sets and uncountable sets. So a set is either finite or infinite, and we will distinguish between two types of infinite sets. So a set that has the same cardinality as n is called a countable set. So what this is saying is that we can make a bijection from the set to the natural numbers. We can do this pairing. So as an example, the set of natural numbers and the set of even numbers, we established a bijection between them, right? So these two sets have the same cardinality, and so these are both countable sets. Another way you want to think about countable sets is that these are listable sets. You can enumerate all the elements in the set. You can actually list them out, like 2, 4, 6, 8, or for example the odd numbers, you can list them out, or even the integers, you can list them out. For example, 0, minus 1 plus 1, minus 2 plus 2. So these are all examples of countable sets. Any set that can be listed, you can put into a bijection with the natural numbers. Now an infinite set that is not countable, that cannot be listed, is called an uncountable set. With these definitions in mind, we begin by showing that the open interval from 0 to 1 is an uncountable set. That is, the cardinality of the open interval from 0 to 1 is strictly larger than the set of natural numbers. There is no bijection or one-to-one correspondence between these two sets. There will always be elements left over in the open interval from 0 to 1 if you try to make this correspondence. To prove this result, we will argue via contradiction. We will suppose, for contradiction, that the open interval from 0 to 1 is countable. That means that there is a bijection going from the set of natural numbers to the open interval from 0 to 1. There is a one-to-one correspondence between these two sets. Like I mentioned before, this simply just means we can list out all the real numbers in the open interval from 0 to 1. So I can go ahead and list out the first number in this open interval, the second number, third number, and so on. So I can make a list of every number in the open interval from 0 to 1 right here. Now let's consider the decimal expansion of each of these xi's. So each of these xi's is a number from the open interval from 0 to 1. So its decimal expansion will look something like 0 point and then a bunch of digits. Each of them will look like this. Now we will construct a brand new number, let's call it x, that will also be in the open interval from 0 to 1. So it starts with 0 point, and then its digits are b1, b2, b3, and these bi's are defined by the following rule. So the nth digit in the decimal expansion of this number x is given by the following rule. What we do is we look at the diagonals. So we look at the first digit of the first number, we look at the second digit of the second number, we look at the third digit of the third number, and we just see, is this number 1? Well, if this number is 1, I will put a 2. If this number is not 1, I will put a 1. Now the choice of 1 and 2 is actually arbitrary. You could have picked 3 and 4, or 0 and 9, or you could even increase it. So whatever this number is, you make it plus 1. And when you get to 9, you wrap back around to 0. To make this a little bit more concrete, let's take a look at an example. So let's suppose x1 happens to be 0.173 and so on, x2 happens to be 0.000 and so on, x3 happens to be 0.912 and so on. Now how do we construct this new number x? Well, what we do is we look at the first digit of the first number, and then we look at a rule. Well, in this case, that digit happens to be a 1, so we just put a 2. Then we look at the second digit of the second number. Well, in this case, it's a 0, right, which is not 1. So what we put is 1 here. Then we look at the third digit of the third number. Well, it's a 2, which is not equal to 1. So our rule tells us that we need to put a 1. And we go in this manner. Now, what's special about this construction, this constructed number x, is that x differs from xn in the nth decimal place. So what I mean by that is the number x, well, it differs from x1 in the first decimal place. It differs from x2 in the second decimal place. It differs from x3 in the third decimal place by the way we constructed it, right? We always check what is the nth digit of xn, and then we make it different, right? And so what we see is that this number x, it's an element of the open interval from 0 to 1, but it's not a part of our list, right? So we ended up missing this number. And so this contradicts that we actually listed out all the numbers in the open interval from 0 to 1. So what this means is that there is no bijection between the natural numbers and the open interval from 0 to 1. There will always be numbers left out on our list. Now that we have shown that the open interval from 0 to 1 is uncountable, let's show that the set of real numbers is uncountable. That is, the entire open interval from minus infinity to infinity, the entire real number line is uncountable. The way we will do this is actually by constructing a bijection or a one-to-one correspondence between the open interval from 0 to 1 and the set of real numbers, because we know that the open interval from 0 to 1 is an uncountable set. So if we can show that the open interval from 0 to 1 has the same cardinality as the entire real number line, then we can conclude that the set of real numbers is uncountable. And the way we will do this is by constructing an explicit bijection. Consider the following function f, which maps the open interval from 0 to 1 into the set of real numbers, and the rule is given by the following function, 1 minus 2x divided by x times x minus 1. I have a rough visual of what this function looks like. So we can see we have asymptotes at x equals 0 and x equals 1, and the function is bound between these two asymptotes. And what we see is that the function is strictly increasing. So since the function is strictly increasing, distinct inputs will map to distinct outputs, right? As you increase from 0 to 1, you will see that the outputs will increase from minus infinity to positive infinity. So that's how we will argue that the function is injective. And the function is also surjective, because if you pick any real number y, let's just say we pick this real number y, then there will be a corresponding input that maps onto that real number y. So the main takeaway is that the open interval from 0 to 1 is getting mapped onto the entire real number line from minus infinity to infinity. Now, to prove this a little bit more formally, we will need a little bit of calculus. To show that the function is injective, like I mentioned, we will show that f is strictly increasing. To show that f is strictly increasing, we will take a look at its first derivative and show that that function is positive, because the derivative captures the rate of change, or the slope. If we can show that the slope is always positive, then that means that the original function is strictly increasing. So using the quotient rule, we can find the derivative of f, and you can see that the denominator is squared, right? This term is squared, so it's non-negative. So what we really have to take a look at is actually just the numerator. So the numerator can be cleaned up into the following quadratic. And now what we have to do is check, when is this bigger than 0? We have to solve the inequality, when is this quadratic bigger than 0? There's many ways you can do this. You can, for example, write this in vertex form. But the way I did it here is by finding the discriminant. So the discriminant tells us how many real roots a quadratic has. So in this case, the discriminant, which is b squared minus 4ac, happens to be negative. This indicates that there are no real roots. Also, this parabola has a positive coefficient, which means that it opens upwards. So if the parabola is opening upwards and it never touches or even crosses the x-axis, that means this quadratic is actually strictly positive. It's always going to be above the x-axis for any real number x. And so therefore we can conclude that the derivative, the first derivative f prime of x, is strictly bigger than 0. It's strictly positive for all x in the open interval from 0 to 1. And so this shows that f is injective. Next, let's show that f is surjective. To do this, we will consider what happens as we take the limit as x approaches 0 from the right hand side, and we will consider what happens as we take the limit as we approach 1 from the left hand side. So as we approach 0 from the right hand side of this function, you can plug in 0, you'll see that we get a non-zero on the top, we get minus 1, and we get 0 on the bottom. So this gives us minus infinity. And if we approach 1 from the left hand side, then we get actually a positive result on the top. We just get 1, and on the bottom we get 0, so that gives us positive infinity. We can show this more formally using the epsilon delta definition, but that's not really the point of this video. Now we also know that f happens to be continuous on the open interval from 0 to 1. Well, why is this the case? It's because f is actually a rational function. It's just a ratio of two polynomials. So these functions are actually continuous everywhere on their domain. And this domain is defined as long as the denominator is not in 0, and we saw that the denominator is only 0 when x equals 0 or x equals 1, which are not in this interval. So therefore f is continuous on this interval, and so by the intermediate value theorem, f will actually take on all values from minus infinity to infinity. In other words, for every real number y, there exists some input x from 0 to 1 that maps onto y. And so this shows that f is surjective. So this actually does indeed show that f is a bijection. And so therefore we conclude that the cardinality of the open interval from 0 to 1 is equal to the cardinality of the set of real numbers. And since the open interval from 0 to 1 is uncountable, we conclude that the set of real numbers is also uncountable. This brings us to the end of this video. If you found this video helpful, I would really appreciate it if you could leave a like, and I would encourage you to subscribe for more math videos. Thank you.